Good morning, everyone. Welcome back to some physics practice in our favorite textbook. Introduction to Mechanics, second edition. All right, so today I will be presenting problem 7.4. Nice and early, as you can see, 7:30 a.m. No, I did not get up this early. No, I did not get sleep. But that's quite all right. I will get some sleep after this. 7.4, very interesting problem. Before you attempt this and before you watch this video, I do recommend in the textbook, take a look at example 7.7. It's on page 254. I recommend that as a sort of a corollary example to this question. It's very similar, and it may help you in understanding what this question is asking and maybe get you started in solving it. So I recommend looking at example 7.7 on page 254. But for now, we're going to get solving 7.7 here. So 7.7 says, a spaceship is sent to investigate a planet of mass m and radius r. So let's draw our planet. Okay, it's got a mass m and a radius r. This is how they've drawn it in the book. Radius r like that, okay. And it says, here's our axis. You might think, our axis, okay, well, it's not really an axis of rotation, but it says that while hanging motionless in space at a distance 5r from the center, okay, so here, this distance here, we'll do some engineering notation. Ugh, that's 5r. Okay, and we're going to launch it says we're going to launch a package that has a mass small m, which is much smaller than the mass of the spaceship. For what angle theta will the package just glaze the surface of the planet? So we're launching a package at an angle theta and at a speed v0 from our spacecraft. I don't know. Let's draw maybe make like a stupid cartoon spacecraft that's it's in space, but it's still exhausting stuff. All right. So anyway, and we're launching some kind of little package with mass small m from that. Okay. So and the question is, for what angle theta will the package just graze the surface of the planet? All right. So you can imagine some trajectories kind of curving toward the planet here. And for what angle theta will it just graze it? So, well, we can imagine theta 90 degrees, probably not going to graze it, right? Theta 0 degrees, kind of a direct hit, right? Gravitational field will only help with that. So really what we're asking when they say for what angle will it just graze it, it's find the max value of theta. Right, because we notice that it will not graze with a greater value, but the lesser we go as we approach 0, it will most definitely, well, it won't graze the planet. It'll, fucking go head on, right? Battering ram into it. So find the max value of theta is what we're looking for. That will cause a collision. And you might be thinking, well, why is this in this section? Why is this in the conservation of why are we talking about linear momentum and all this? And it's because using conservation of linear momentum can actually help us here a lot in simplifying this problem. And we're going to see how to do that. So remember, we're treating this package that we're launching from the spaceship as sort of a point-like particle, right? It's got mass little m that's much, much smaller than the spaceship. And, I mean, we're to assume that, the mass distribution doesn't matter. It doesn't tell us anything about the mass distribution. So it's a point-like particle, right? So the first thing that I'm going to start every problem with, or most of them at least, is that, yes, indeed, the conservation of angular momentum is held in this problem. You may say, wait, but Matthew, you might say, what about the gravitational field, right? What about isn't that an external force on this system, right? And to that I would say, and then of course the argument is, well, this body is part of the system, and so it's not an external force. But really the best argument is that the force of gravitation always acts in the r hat direction, right? Where r hat is the radial, well, it's actually the radial inward, right? Because the force is acting inward to a gravitational body. So if it's always acting inward, let's say that somewhere along the trajectory our mass gets here, right? Our gravitational force, this is force gravity, is always going to act inward. And you might say, okay, well, so what? What does that mean? Well, because it's always going to act in the radial direction, directly outward, it's actually never going to apply a torque on the system. It's never going to change the rotational, or the angular momentum. It will change the linear momentum, sure. In fact, we'll see that the object accelerates as it gets closer and closer to the planet. But it will not change the angular momentum. And we can see why if we investigate the equations a little bit. So we know that torque is a way to change the angular momentum. It's a way to essentially apply an angular force, if you will. And it's equal to the radial vector, some people call this the lever arm, crossed with the force that's applied. But wait a minute. What is a cross product? A cross product is really just the magnitude of one times the magnitude of the other times sine of the angle between them. Okay, but wait a minute here. This force that we're investigating is force gravity. And this radial vector, that is the vector that force gravity is acting upon. I mean, they may be different magnitudes, right? You may want to normalize this one, or gravity might have some different magnitude, but they are collinear with each other. They're either collinear or they're either collinear or antilinear. So they're either going this way, one on top of the other, right? Or they are going one this way and one this way. Either way, sine of pi or sine of 0 is still 0. So the torque is equal to 0 by gravity. So the force of gravity, because it's always acting in the radial direction on this package, is going to exert a net zero torque. And therefore, the conservation of angular momentum can apply to this problem. And if you had read example 7.7 in the textbook, that would have made this very clear. And it's a very useful fact for forces like this. I'm sure we'll see this again in like Coulombic attraction in E&M, right? Angular momentum will be conserved because you have Coulombic attraction is also an inverse square law. It's also acting in the radial direction. But like they mentioned in the book, we might not find this property for something like magnetism, right? Where magnetism, the force is dependent on the velocity of the particle, and it gets all complicated. But that's not what we need to know right now. So let's take a look at how we can solve this problem doing that. So that's just an intuitive explanation. Well, it's, I guess it's more of a symbolic explanation using the equations of why we can assume that this momentum is conserved. And it's a beautiful fact that angular momentum is conserved, even though linear momentum is not. So L initial is equal to L final. Well, what's L initial? What's L initial? Okay, so we know, so this is a particle, right? This is a point-like mass. So we know that L initial is going to be equal to the radial vector initial crossed with the momentum initial. Okay, so what's the radial vector now? Well, the radial vector, that's going to be this guy right here, right? And we've already measured it. We've already measured it here, maybe as an engineer would, with like a ruler or something. And here, we know that that's that vector going there, right? So that's going to have, I'm just going to use the another definition of the cross product. So the magnitude of that is going to be 5r, or I should say, is equal to the magnitude of those two times sine of theta. So I'll write that as 5r is the magnitude of the first one. And then what's the magnitude of pi? Well, it's going to be the small m times this v naught, right? That's the definition of linear momentum, mass times velocity. And then we have to find the angle between them, sine theta. But look at how the diagram's drawn. The diagram already has this theta set up in a pretty nice place for us, right? So theta is actually going to be the angle between this this radial vector here and this vector coming out here. So it's already going to be the angle between them. Now, one thing you might ask is, you're saying, okay, well, the radial vector is usually drawn from the center going outward here, right? And maybe I'll do this in a different color because it's kind of a bit of a tangent that we're going on here, but it's important to understand. This radial here is really going out like that. That's the radial vector. And our momentum vector is really going like that. So if we were to draw both of them on a coordinate plane, we would see vectors that look like this. We would see one that looks like this. That's our radial initial. That's Ri. And then if we were to draw another one, we would see that it looks kind of like this. And this is our Pi. And so you say, okay, well, clearly here the angle is theta, but that would be if I drew my r vector from the object to the center of rotation. But that's usually not how the r vector is explained. The r vector is usually originating at the center of rotation and going to the object, right? So you think, you know, either I could just gloss over this and keep going, or I could think deeper, and I encourage you to think deeper. And so I paused for a moment and I thought about this, and you'll notice sine theta, I mean, it changes based on which one you're going to do, right? So this here, that's a theta between those two vectors, but look, that theta is an obtuse angle, and this one is an acute angle, right? So the question naturally becomes, which one do I use? And really this all comes down to sine being a periodic function that is both positive and negative, right? So if you're worried about this and you're thinking, which one do I use? The question isn't really which one's right or wrong. It's more of how you handle your negative signs, right? Because sine, I mean, if you were to draw a graph of sine, right? If you were to draw a graph of sine, well, sine, if we're taking an input as an angle, well, we want to start by saying the vertical component starts low and then it goes high, reaches a maximum, and it goes low again, right? And then there we go. That's one period of sine. And so you notice this whole idea, right? This whole idea of, okay, the vectors here, sine is very, very, very small, and so the vectors are perfectly aligned. And so we're not going to give the cross product much weight. And then you go up here and you go, okay, here's pi over 2. Look, they're 90 degrees from each other. So we're going to give the cross product the maximum weight possible. And then you keep going and you get, so this is the maximum weight possible would be if pi was there, right? And then you keep going, and you see the same pattern, but it's negative. So then here, we would see something analogous. Let's use green, because we used green for the pi here. So then maybe somewhere here, right? You would see that we are getting somewhere here maybe. Right, and then as we go all the way to R1 going to the left and pi going to the right, we reach this point here, which is where theta equals pi, right? And so you notice that this graph here is symmetrical about pi over 2, at least in this domain. So because it's symmetrical about pi over 2, it really doesn't matter which way you think of it, whether you think of the angle here or the angle here. It's symmetric about pi over 2. So that was just a little tangent in case you're worried about that. And these are questions that are worth thinking about, that are worth exploring, and that are worth going into, because this is certainly something you want to be thinking about now and getting clear now in your head before an exam or before you're working on your homework. So let's continue with our problem now that we've discussed what angle to use with this cross product. So we can use just this angle, and as I proved, because of the symmetry of sine around pi over 2, it's the same thing as the other angle presented. Now, here, this is the initial angular momentum. So let's go ahead and find the final, right? Because we know it's conserved. So I mean, next step is find the final, right? Let's go ahead and do it. So the final one, right? Well, the final one is going to be R final cross P final. Let's think about this. Okay, well, what's changed in R? Well, obviously, R is the vector. R is the vector coming out of the center of this mass and going to our package. So R final, if you imagine the mass's trajectory coming up here, and perhaps this wasn't drawn. Yeah, that was the force of gravity. So let me just erase that so that we can draw its trajectory. So if you imagine the trajectory of this thing just barely kind of grazing the surface and hitting, then we see that R final looks something like, I don't know, my pen won't change color. R final, here we go. R final looks something like that, right? So that's our R final. Now P final, what is that going to be? P final. Well, the mass isn't going to change, but we did talk about before that because we have gravity acting on it, although angular momentum is conserved, linear momentum isn't necessarily conserved. So the linear velocity in this linear momentum term is going to change. So we're going to have to account for that. So let's just write this in using this formula here, right? So what is the magnitude of this radial vector going to be in the final time of the time period that we're exploring? Well, the final time that we're exploring is during the impact. So during the impact, the radial vector is going to have a magnitude of capital R. That's the radius of the planet. It's going to impact the planet a distance of capital R away from the center of mass of the planet. So here, I'll write, it's the magnitude of this first vector, R, times the magnitude of the second vector, which I'll write as M. That hasn't changed. But V, I'm going to have a subscript F for final, because we know that that's going to be different than the initial velocity, because gravity's been acting on it. And now, what is the sine of the angle between them? So here, I'm going to use phi, because we've already used theta. So here, notice what's going to happen. We know that as it just grazes the circle, circle, sphere, whatever you want to call it, as it just grazes the planet, we know that the momentum is going to be tangent to the circle, right? And we know that a radial line is always perpendicular. It's always 90 degrees with a tangent line. So here, this red one here represents P final, and this red one here represents P initial. Future Matthew here. Just wanted to let you know, I accidentally drew this as the initial linear momentum, P initial. It's supposed to be the final radial vector. That's pretty obvious. I don't know why I slipped up there. We know there's going to be 90 degrees there. And so we know that this is going to be sine of pi over 2, or 90 degrees. Which is just equal to R M V final. Right? Because sine of 90 is 1. So, Now we can use the conservation of angular momentum to set up a important equation. We can just set these two equal to each other. We can say that 5r mv naught sine theta is equal to r mvf and just times 1, right? Okay, so obviously there's some simplification that can be done here. We're assuming that the radius isn't 0, because, I mean, come on, right? What's the point, right? So the radius isn't 0. We're also assuming the mass is not 0. So therefore, we can just divide both sides by 1 over the radius times the mass. And here we get 5 v naught sine theta is equal to v final. Okay, interesting. So we don't know what sine of theta is, and we don't know what v final is. So this is begging for another equation. We have one equation and we have two unknowns. We know v initial. I mean, we don't know the numerical value of it, but who cares, right? We know that it's a given. But these two, we don't know the sine of theta term, and we don't know this v final term. So this is begging for another equation. And what we're going to use to get that other equation is conservation of mechanical energy. So we're in a gravitational field, and what do we know about gravitational fields? Well, they're conservative fields, right? They're conservative fields. So your potential energy is merely a function of your position in that gravitational field. And since we know our initial position and our final position and all the masses of bodies involved, we can calculate the change in gravitational potential energy. And remember, gravity is assumed to be the only force acting on these bodies. So the change in gravitational potential energy is going to be equal to the change in kinetic energy. We're converting the gravitational field's potential energy as we move closer and closer to the planet into kinetic energy. So we're going to use a conservation of energy equation in order to give us something more to work with here. And the key to solving these problems is realizing, cool, I have this relationship, but I have one unknown, I have two unknowns. I'm going to need another equation, right? The amount of equations you have is the amount of unknowns you can solve for in a system of equations. So let's go ahead and find that other equation. And in this case, what we're going to do is we're going to investigate the change in gravitational potential energy. So let's just go ahead and think about that for a moment. So if my pen will select, there we go. So the change in gravitational potential energy is equal to, well, the gravitational potential energy final minus gravitational potential energy initial. Okay, so what's the final gravitational potential energy? Well, we know gravitational potential energy is just G mm over r, right? And you can use Newton's law of gravitation and what's it called, the work energy theorem or something, and just a basic integral to derive this. But force times distance, right, where your distances are and you're integrating. And then you change the r squared on the bottom to an r to the first power, and that's how you get your gravitational potential energy in joules. So that's the formula. Probably should have this memorized. If not, Newton's law of gravitation, you can derive it there, work energy. So this here actually is our gravitational potential energy final, because we are going to be in the final time step of this time period that we're analyzing. How far are we going to be away from the center of mass? Well, we're going to be a radius r. It's going to be a radius r. So it's merely going to be, this is negative G m over r, okay? And then we'll subtract what is our initial gravitational potential energy. Well, the distance is actually now is 5r if we look at the diagram. So initially we started here, and so the radial distance here is 5r as we've denoted below. So initially the initial gravitational potential energy. Oh my god, Microsoft Whiteboard, please, for the love of all that's good in the world. Alright, so that's 5r here, and same factors, g, m, little m. Okay, so that's the change in gravitational potential energy. And you can simplify this, get some common denominators, right? Make sure that 5r is a common denominator. And you get that this is equal to negative 4g m over 5r. Now, this here, this result, why is it negative? Well, the gravitational potential energy, right? This is change in gravitational potential energy. That's why we did final minus initial. And so we are losing gravitational potential energy, right? And where is the energy going to? Well, we know that mechanical energy is conserved in this system, so that energy is going to kinetic energy. So now we can just say that the change in kinetic energy is equal to the negative change in gravitational potential energy is equal to 4g m over 5r. Now, what is the change in kinetic energy, really? Let's go ahead and write out the formula for kinetic energy in this system. So, I'm really trying to scroll down here. There we go. Okay, it stopped lagging. All right. So, here, if we're to write it out, really what we're saying with this formula here, if we make it more verbose, is we're saying that the kinetic energy initially plus this amount of energy we've gained, remember these are both in presumably joules, so we can just add them like this, is equal to the final kinetic energy. And we get this nice equation where we can then solve for V final, right? Now there's a few things we can do. We can factor out a little m out of all the terms and cancel them. So we can do that pretty easily, right? So we can do that. We can also, oh, I forgot 1/2 here. We can also multiply all terms by 2. So we'll go ahead and do that. So we'll factor out and divide by a little m. We're assuming that's non-zero. And we'll multiply everything by 2. So we get, actually we just get V naught squared is equal to, now we're multiplying by 2, so we get 8g capital M over 5r is equal to, here we're multiplying by 2, so that goes away. The little m goes away, is equal to V final squared. There we go. Okay. So, what happened here? Oh, this was not an equal sign. This was a plus sign. My bad. So we get this equation. This relates the initial velocity to the final velocity. So solving for the final velocity, we get is equal to, now, the square root of V naught squared plus 8g m over 5r. Now, this here, this V naught, we're going to keep it in this form for right now, but we're going to plug it in. We're going to see that we can actually perhaps make it a little bit simpler. So this is V final right now. Okay. So let's keep this in our mind that this is V final, what we have here. So I'll go ahead and just box it so that we remember that that's our V final in terms of our V initial and our change in gravitational potential energy. So now we can use this equation here. So this one was the one that we got from conservation of angular momentum. And now we're going to plug in this V final that we received in terms of V initial and other variables that are known in order to solve for this unknown. So 5V naught sine theta is equal to V final. So 5V naught sine theta is equal to V final, which is the square root of V naught squared plus 8g m over 5r. Okay, there we go. Now we're looking at this and I'm thinking, Well, it would be nice if we could get the v naughts together, right? It would be nice if we could get the v naughts together. That would be nice. So I'm looking at this and I'm thinking, well, you know what? We could actually, I'm running into some other work here. Hold on, let me erase some things. There we are. Okay, so I've erased some other work I had going about Gauss's law on my whiteboard, so we have some more room to continue this problem. So, like I was saying, I'm noticing these v naughts here. Be nice if we could group them together, right? We can't exactly, like, you know, I'm assuming you guys know square root rules, right? You can't just like take this out. That's not really how it works. It's got to be a factor of everything. But what we can do is we can say, well, you know, what would kind of work is, and once again, this is just a simplification step, right? So it's not all that important, but you want to get all your points on your homework in your exams. So you want to try and simplify as much as possible. So when I'm seeing these two variables and I see this is under a square root, it's like, oh man, it's almost squared. If only that was squared, I could kind of divide both sides and do all that business, right? So actually how I'm going to write this is, first I'll divide both sides by 5 v naught. So I'll write that out. So 1 over 5 v naught. Okay, so now we have sine of theta, and this is good now that we have sine of theta on one side, because then we can just apply arc sine to get theta, right? So sine of theta is equal to, and then here, 1 over 5 v naught times this business. Okay, now the thing about this is, let me just beg the question, what if you wrote it like this, 1 over 5 v naught, square root here, and what if I just factored out a v naught squared here? So that would be 1 times v naught squared for this first term. In the second term, we don't want to multiply by v naught squared. So what we're going to have to do is we're going to have to divide by it. 8gm over 5r v naught squared. And then the beauty of this is we can then, since everything in the square root is multiplied by v naught squared, I'll write it out even more verbosely so that it makes a ton of sense. This is really just saying v naught, right? v naught times v naught, 1 plus 8gm over 5r v naught squared. And so this we can pull out here. And look at the beauty of that. If we can pull out a v naught there, that cancels with this v naught on the denominator. And so we just get 1/5 times the square root of 1 plus 8gm over 5r v naught squared. Now, you know, I guess there could be an argument made about maybe you want this to be simpler because you don't want your v naught term over here, but I like how it cancels when you pull it out. And remember, all of this is equal to sine of theta. Now, it asks for what is sine of theta, right? What is, and let me make sure that that is indeed what they are asking for. For what angle theta will the package just glaze the surface of the planet? Okay, so we have this. We have sine of theta. How do we solve for theta? How do we solve for theta? Well, we can use our inverse trigonometric functions, right? So arc sine of theta is just equal to theta. These kind of undo each other, right? It's like raising an e to a logarithm. They undo each other. They are inverse functions of each other. But if we take the arc sine of one side, we have to take the arc sine of the other side as well. So theta is equal to, and let me write this on a new line here so it's nice and neat. Theta is equal to arc sine, or sine inverse, whatever you want to call it, of 1/5 the square root of 8gm over 5rv naught squared plus 1. And there you go. There is your theta. So, hope you found this problem helpful. Hope you found some of the explanations useful in your understanding. If you're having trouble with this problem, I do recommend looking through how they worked through example 7.7. Remember, all this builds on itself, so your conservation of mechanical energy and the fact that the gravitational field is a conservative field is going to be helpful in solving these problems as well, because they're going to start to mix topics as we've seen here. But the real point, and I think the thing that really hits home in this problem here, is the fact that if you have a force that is acting along the radial vector, if you have a force that is acting it's not parallel, but is coinciding with the vector that you use for your radius in these cross product calculations, you're actually not going to change the angular momentum. Because if you do have a force that is coinciding with your radial vector, then as we showed earlier, we did a brief calculation at the beginning of the video with torque, and we showed that it would actually apply zero net torque, because torque is a cross product of R and the force, and if R and the force are aligned, you're actually going to have no torque and therefore no change in angular momentum. So this is a problem where, although linear momentum is not conserved, I mean, there's a gravitational field acting on it that's increasing the momentum, and that is a force applied. The angular momentum is still conserved because that force only acts radially, and so that's really an important point that this problem is trying to really close in on. So I hope that helped. I hope that helped for 7.4. I am working on. There seems to be a dilemma. Well, it doesn't seem to be. To me, there seems to be a dilemma with, I think it's 7.2. So yeah, if I haven't posted a video on 7.2 yet and someone wants to talk to me about it, feel free to DM me, because that one is giving me hell. This 7.4 though, not too bad. And more K and K to come. See you next time.